Good morning, everyone. I'm Luca Piazzon, and unfortunately, I can't be live with you today. So we decided to go for a recorded video, but feel free to contact me if you want to know more about this work or if you have any questions. I will present the work done together with Nicola Ferro and Marco Ferrante named S-Aware using crowd judgments in supervised measure-based methods for IR evaluation. This is an extended abstract of the work recently presented at the Conference and Labs of the Evaluation Forum in September 2020. And the goal of this work is the development of a set of supervised algorithms for the usage of crowd-assessed judgments for the evaluation of information retrieval systems. In this presentation, I will first introduce the motivations behind the usage of crowdsourcing methods, passing then to the description of our algorithms, of the experiments and the relative outcomes. In the field of information retrieval, a good method to evaluate information retrieval systems is crucial for their improvement. To do this, it is necessary to use experimental collections, where for each document is assigned a relevance judgment, usually given by an expert assessor. This classical methodology for test collection creations is, however, quite onerous in terms of time and costs. A modern approach instead relies on judgments coming from a larger number of less qualified assessors, called crowd assessors, that are then used together in place of expert judgments. The collection of crowd judgments is largely faster and cheaper, but can be affected by spam judgments. The classic usage of crowd judgments is to combine them at pool level, obtaining a merged pool that can be used as ground truth for the evaluation tasks. Two major examples of these methodologies are majority vote and expectation maximization. Majority vote is the simpler one. For each topic document, pair takes the judgment given by the majority of the crowd assessors. Expectation maximization instead iteratively estimates the probability of relevance of the documents and at convergence assigns to each document the most probable judgment. Merging crowd judgments at pool level has one main weakness. A single error at pool level can cause different effects on different performance measures computed on the run coming from the systems. Let's consider this toy example where there is a single mislabeled document and retrieved at position 2. Here, a single error at pool level that corresponds to a 20% error in the pool can cause errors on measures from 19 to 50%. To avoid this problem, in our methods, we follow a different approach. Instead of combining the crowd assessors at pool level, we compute the evaluation measures based independently on each crowd pool, and we combine these measures, weighting each assessor with an accuracy coefficient that estimates the skills level of each crowd assessor. These accuracy scores can be computed in different ways. In our previous work, we presented an unsupervised version of AWARE, and the information retrieval systems were evaluated according to each crowd assessor and according to 3 fake random assessors that randomly assigns a relevance judgment to a document with different probabilities. These measures were compared using some dissimilarity measures. So the more the crowd assessor behavior is far from the random ones, the higher accuracy is assigned to the assessor. In our work, instead, we used a set of supervised estimators of crowd assessor accuracy. In this case, the crowd assessor measures are compared on a training set of topics with the measures computed on the gold pool. These measures are compared using some similarity measures. So the more a crowd assessor is near to the gold standard behavior on training topics, the higher accuracy is assigned to the assessor. We consider the values of an evaluation measure computed on a set of runs coming from a set of information retrieval systems for a set of training topics, and we denote this as M. And we consider also the measures computed with respect to the gold standard, and we denote this as M star. We propose two approaches to compute the similarity between the assessor and the gold standard. The first one is to compute the root mean squared error between the assessor measures and the gold measures. Small values, or RMSE, are mapped to high accuracy values. The second approach involved the ranking of the systems induced by the computed measures and computes the Kendall-Stowe correlation between the assessor ranking and the gold ranking. We consider then three levels of sharpness of the accuracy scores, taking the square and the cube values to increase the discrimination among good and bad assessors. To test the effectiveness of our methods, we compared them against some common methods as majority vote and expectation maximization, the Georgescu-Zhou algorithm that uses the expectation maximization to predict assessor confidence, the Tangley's semi-supervised version of expectation maximization that makes use of a set of gold labeled documents, the uniform aware method that assigns the same accuracy to each assessor, and the best performing unsupervised aware methods. We use the average precision as evaluation measure. We use the runs coming from track 8, track 13, and track 26 as systems, and we combine groups of 2 to 7 assessors. Since gold training data is expensive to obtain in a real case scenario, we use a very challenging fraction between training and test set, using only 30% of the documents as training set. The experiments are performed considering all the possible combinations of parameters and repeated 100 times for validation purposes. We use two different datasets. A first set of assessors comes from the participating pools of track 21, and we have 31 complete sets of judgments of 50 of the topics used in track 8 and track 13. To better fit to a real case scenario where each crowd assessor judges only a portion of the dataset, we considered also a set of artificially partitioned assessors, each of them taking judgments from different original crowd assessors, simulating a more fragmented situation. The second dataset is the one assessed by Inet et al. That collected judgments coming from 406 assessors on track 26 topics. And to use this data in our experiments, we grouped these assessors to obtain a set of partitioned assessors similar to the one I mentioned before. Let's move to the experimental results. Once obtained the final measures according to each method, we computed the p-correlation between the ranking of the systems induced by each method and the ranking induced by the gold standard measures. Let's firstly consider the original complete pools from track 21, that is clearly the most favorable case for S-aware. This plot represents the p-correlation value trends while increasing the number of merged assessors. We see that S-aware with cubed Kendall-Stowe similarity constantly outperforms all the other approaches, even when we combine a small group of assessors. We can observe that Kendall-Stowe performs better than RMC as closeness quantification, and that the cubed weighting typically gains some more performance. Both unsupervised and supervised aware outperform the most part of the baselines. Moving to the partitioned assessor, here we have the plot about the experiments on the Inet et al. Dataset. We can see that in this case the gap between the S-aware and the unsupervised aware becomes smaller, but S-aware still outperform in most cases its unsupervised version. In general, S-aware still outperform both the unsupervised and the semi-supervised baselines. Also in this case, the squared and the cubed version of the accuracy scores achieve a better performance since they emphasize more sharply the difference between good and bad assessors. In this table are reported all the results of our experiments. On the left we have the system, on the top we have all the tested methods. Both values are the best performing methods for each row. We see that in general, S-aware and unsupervised aware are always contending for the first place, and this strengthens our motivations to combine assessor at measure level and not at pool level. Let's go to the conclusions. Even using a very few training data, S-aware mostly outperform all the other tested approaches, but as expected, the capability of S-aware to correctly estimate the assessor accuracy decreases when dealing with the fragmented assessors. Both unsupervised and supervised aware in general outperform all the set of baselines. A future extension of this work on both supervised and unsupervised approaches will try to compute an accuracy score for each subassessor, avoiding the need to group fragmented assessors as we have done here for partitioned assessors. Thank you for your attention.